Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So before we proceed, I'd like to request our members to kindly go to YouTube, search Ernest Sciences and Mathematics TV channel, subscribe to our channel and engage us in the comment section, and also ring that notification bell so that we can be getting updates on our various uploads in mathematics, physics, chemistry, and biology and other related topics. So today we're going to look at the concept of entropy, and we're going to consider a case of entropy change for an ideal gas. So in this case, from the, of course, first law of thermodynamics, we have said that we can be able to represent the change in energy using that specific, or the first law of thermodynamics using this particular representation of an equation, whereby Q is the energy and this is the change in internal energy. This is the heat energy involved, internal energy, and this is the work is going to be accompanying that specific change. And of course, in our first discussion on the concept of entropy, we see that entropy is, of course, a measure of disorder, and we are given a specific equation which, of course, we have said is going to be used in trying to describe this specific aspect of entropy, whereby we see that we can describe entropy as, of course, the ratio between this specific change of Q, the sigma Q reversible over absolute temperature. And this, of course, is going to give us a basis of trying to describe this particular representation. So therefore, for us to, from the first law of thermodynamics, we can be able to see that for us to describe this infinitesimal change, we can be able to give it in this particular fashion, whereby we have Q reversible is equivalent to Cv dt plus P dV. Now, for us to, of course, comprehend this specific representation, we had said that we can be able to represent what we refer to as the molar heat capacity at constant volume, which was given as dE over dt, whereby dE is the change in the internal energy and this absolute temperature. So therefore, this was a ratio that was used to represent dE over dt. So in this particular case, it implies then therefore that dE is equivalent to Cv dt, and of course this is going to give us the concept of the delta E that is involved in this particular case from our first law of thermodynamics. So having stated that, then therefore this is going to create meaning in this specific representation, whereby the delta is going to be substituted for this specific equation in this particular case. And we had said that for us to comprehend on the concept of work, we say that work is basically going to be represented for the case of a compression or expansion of a gas, we're going to consider its pressure that is going to be applied, and of course the volume change. We had said that we can be able from a normal representation for pressure, we say that pressure is the ratio between force over area, and therefore if work is the product of force and the distance covered, we had said that for a compressed gas we can be able to represent this aspect of a force by having pressure times area, and then the difference in that specific compression chamber, which was stated as a H, which is the difference in height. So we had compared a gas chamber which was consisting of this specific portion for area, and this was the difference in the compression or expansion of a gas, which was represented by M. So the element of area and the height is going to give a difference in volume, and therefore we had said that we can be able to, of course, this is a force is a product of pressure times area, but work is a product of force times the distance, which we had said that therefore force can be represented as pressure times area times the height if we are trying to consider a compression chamber that is given as such. So therefore we say that work can be represented as pressure times the change in volume, where AH is going to represent that specific change in volume. So therefore we can be able to do a substitution for work using PD, V given as such. So I hope that we have understood that specific transformation. So therefore we can be able to represent this particular change, which is a sigma Q reversible using Cv dt plus P dV, as I've illustrated on the board. Now this is going to be the case whereby we're going to consider only pressure and volume being involved in this specific change. And we can be able therefore to represent this aspect of entropy that I've referred to as change in entropy ds, which is this is sigma q reversible over t, by transforming this particular equation through a division over what we refer to as the but if we try to consider the concept of an ideal gas, which is our point of discussion, we're going to involve the case of an ideal gas equation, which is given as PV is equals nRT. Now for 1 mole, then therefore we're going to have the aspect of pressure being given as RT over V. And therefore, in our case, this is going to form our pressure that is going to be a second part of this specific equation. Therefore, we can be able to transform this equation. Let's take this one to be equation 1 and obtain equation 2 by having this one Q reversible, sigma Q reversible given as CV dt plus pressure is going to be now given as RT over V, and then this is going to give us a dV given as such, and this is going to form our second equation, which is going to represent that aspect of our pressure as we have mentioned. Therefore, we can be able to represent this specific change in entropy by having this one divided by T, so that we can be able to achieve this specific ratio given as such. So therefore, this is going to imply that we have the sigma Q reversible over T over T over T. Now, from the last bit of this equation, you can see that the T is going to be, of course, changed. And therefore, for us to represent the delta S, which we had said is S2 minus S1, this is going to be given as CV, and then CV is going to be a constant, that's smaller heat capacity at constant volume, and then we're going to have the integral between T1 and T2 of dt over T, which is the second aspect of this specific equation, plus, and then the last one we're going to have the R remaining, and then we're going to have the integral. So this is going to be the dV with respect to, of course, volume. Remember, this T is going to cancel out with this one, so we're going to remain with this version. We just transform it using this, so we're going to remain with this version of the equation. So we're going to have dV over V from V1 to V2, or from V2 to V1, given as such. So then, therefore, we can be able to simplify this specific equation for representation of a change in enthalpy by giving it as CV. So we're going to involve the loss of logarithms, whereby we're going to have it as a natural log over T2 over T1, given as such, plus R. And then for the volume, we're going to have the natural log over V2 over V1, given as such. So this is going to have our representation for delta S, which is a change in entropy for an ideal gas. Therefore, we're going to consider some scenarios of whereby we're going to see that this is going to depend on the initial and the final temperature, especially if we're trying to consider this case. And if we're trying to see, we had mentioned that this is going to be involving volume and pressure, we can be able to see a different version of this specific case for volume and pressure from an ideal gas. So I mentioned and said that we can be able to have this version of the representation as of an ideal gas for 1 mole, given as PV P1 V1 is equals R, which is a constant, plus T1. So in this particular case, then therefore we can have a version of the change in the pressure and volume given as RT2. So if we try to consider those two equations, then we can be able to have a representation for the particular case for a volume, the ratio between the volumes and the other aspect of this equation are being given as T2 P1 over T1 P2 given as such. So which this is going to imply that if we are trying to represent this one using maybe a volume or a temperature or pressure, we can be able to do a substitution in our case for the section of a volume, which is R natural log of V2 over V1, by using this specific substitution that I've mentioned, and that is going to give us a second version of that specific equation, whereby we're going to have it given as we just try to do away with this. So if we try to do this substitution in this, we're going to have the change in entropy represented using CV at the natural log of T1 over T2 over T1, and then this is going to be plus R the natural log of 1. So we're going to do a substitution for V1 and V2 and V1, whereby we're going to have it as P1 T2 all over P2 T1 given as such. So from logarithms, we're going to see that this, of course, for P and T are going to have an inverse proportionality, and therefore we can be able to invoke the concept of separation of this specific two aspects of pressure and volume, and therefore the second part of that specific equation is going to be represented as plus R the natural log of so this is going to be T2 over T1, and then we're going to have it as minus R. So this is a continuation of this particular equation, R the natural log of P2 over P1. So if you try to look at the concept of pressure, I've just reversed the equation, and this is going to give the negative aspect of this specific equation. Now we had said that from discussion of the molar enthalpy of the molar heat of capacity, or the molar heat that we had represented as at constant volume was going to be represented using a particular ratio, and we had said that we can be able to represent the molar heat capacity at constant volume and the pressure using this specific ratio, whereby the relationship between the CV and CP can be given using CV plus R is equals CP given as such, and therefore we can be able to do a particular substitution, especially whenever the temperature is going to be constant in this particular case, whereby we're going to see that this can only be represented using the aspect of the first equation and the pressure, and this is going to be referred to as isothermal change, and this of course it's going to be done in another video so that we can be able to minimize this particular aspect of maybe having them together. So I'm going to do a second bit of it in order to illustrate on the concept of isothermal change, the isobaric change, which is going to involve the constant pressure, and then lastly we're going to see isochoric change, which is going to involve a constant volume. So catch us in our next videos. We're going to do the final bit of this particular aspect in consideration of those three states for isothermal change, isobaric change, and isochoric change respectively. But of essence for us is to know how we can be able to represent the change in entropy using these various aspects, considering the temperature, volume, and the pressure respectively. So that is it for now, guys. Kindly catch us in our next video so that we can be able to finalize on the same on these three specific conditions that I've mentioned. So that is it for now, guys. Bye, God bless you.